All right, let's dive into one of the biggest challenges in trigonometry, word problems. In this explainer, we're going to build that crucial bridge, from the abstract triangles you see in your textbook to actually measuring things in the real world, like trees and even airplanes. So let's get into it. Have you ever just stared at a word problem, the one about a surveyor or a boat, and just thought to yourself, where is the triangle? If you have, trust me, you're not alone. It's probably the most common point of frustration, but by the end of this, you're going to be fluent in the language of applied trig. So our first goal here is to basically develop a new kind of vision. It's the ability to see the hidden right triangles that are all around us in pretty much every real-world situation. And that is our mission today. We are going to take those descriptive, sometimes confusing English sentences and translate them into the language of math, specifically into SOHCAHTOA equations. This is how we take the theory and make it real. Okay, so how do we do it? How do we make that translation? Well, it all comes down to one fundamental idea. Seriously, if you can master this one single rule, you will have the master key to unlock every single one of these problems. And this is it, the horizontal rule. Before you draw anything else, before you even think about numbers, you have to establish this line of sight. Just picture an imaginary laser beam shooting straight out from the observer's eye, perfectly parallel to the ground. Every single angle we are about to discuss starts from this one non-negotiable line. Okay, so once you've got that horizontal line locked in, all these problems are going to involve one of two types of angles, an angle of elevation or an angle of depression. Now, they seem like opposites, but as you're about to see, they're connected by a really brilliant little geometric trick. Now let's break this down because this is super important. The angle of elevation, that one's pretty straightforward. You start at your horizontal line and you look up. The key detail here is that it always sits inside the bottom corner of your triangle. But the angle of depression, that's the tricky one. You start at the horizontal and you look down. But notice this, the angle actually sits outside the top corner of your triangle. That little detail is what trips everybody up. And here it is, the big secret. Think about a lighthouse keeper looking down at a boat. That horizontal line of sight from the lighthouse, it's parallel to the surface of the ocean. And because of that, a cool rule from geometry called the alternate interior angles theorem kicks in, and it proves something amazing. The angle the keeper looks down with is the exact same as the angle a sailor on the boat would look up with. So here's the bottom line, the big takeaway. When you're actually solving the triangle, the angle of depression and the angle of elevation have the exact same value. This isn't just a helpful hint, my friends. This is your secret weapon for setting up your diagrams correctly every single time. All right, enough theory, right? Let's put this into practice. We're going to take our horizontal rule and our secret angle trick and put them to the test with 3 real-world problems. Let's see how it works. Okay, first up, a surveyor is standing 150 feet from a giant redwood tree. They measure a 62-degree angle of elevation to the top. So, we draw our triangle. The ground is the base, 150 feet. The tree is the height, we'll call it y. From our 62-degree angle, we're looking for the opposite side, the tree's height, and we know the adjacent side, the ground. Opposite and adjacent, that sounds like TOA from SOHCAHTOA. So, we're using tangent. You just set up the equation, punch it into your calculator, 150 times the tangent of 62 degrees, and boom, you get your answer. That redwood tree is about 282 feet tall. Simple, clean, correct. All right, now for a classic angle of depression problem. We've got an airplane cruising at 30,000 feet. The pilot spots our runway, and the angle of depression is 12 degrees. Now here's where we use our trick. Don't even think about drawing that 12-degree angle outside the triangle at the top. No, we use our secret weapon and put that 12 degrees inside the triangle, down at the bottom corner on the ground. From that new angle, the plane's altitude is the opposite side, and the ground distance x is the adjacent. And look at that, it's a tangent problem again. So, we set up our equation. This time, x is in the denominator, so we do a little bit of algebraic shuffling. It becomes 30,000 divided by the tangent of 12 degrees. The result? That plane is over 141,000 feet away from the runway horizontally. Okay, one last example. A wheelchair ramp goes up 3.5 feet over a distance of 40 feet. Building code says the incline can't be more than 4.8 degrees. So, does this ramp pass inspection? This time, we know the sides, but we need to find the angle. And that is your big clue that you need to use an inverse trig function. It's basically like asking your calculator, hey, what angle gives me this specific ratio? We've got the opposite and adjacent sides, so we'll use inverse tangent. We plug that ratio, 3.5 divided by 40, into our inverse tangent function, and the calculator spits out an angle of 5.0 degrees. Well, since 5 degrees is more than the 4.8 degrees safety limit, this ramp is a violation. Looks like somebody needs to call the architect. Let's wrap this up by focusing on the single most critical takeaway from all of this. This is about how to avoid the number one trap that students fall into, the mistake that guarantees you get the wrong answer before you even pick up your calculator. You know, the source material puts this so perfectly that I just want to read it out loud. It says, "The deadly depression sketch trap. This is the single most failed diagram operation in trigonometry. It all comes down to where you draw that angle." Okay, look at this comparison very, very carefully. The incorrect way, on the left, is what feels kind of intuitive, right? Just jamming that depression angle into the top corner of the triangle. But that's totally wrong. The correct way, the method that will save you every time, is on the right. Always, always use our trick. You take that angle of depression value and you simply place it in the bottom interior corner. That one simple move guarantees your setup is perfect. So what did you really learn today? I mean, this isn't just about passing a math test. The logic you now understand is the very same logic that allowed the ancient Greeks to measure the size of our entire planet. It's what lets sea captains map the New World, and it's what currently guides the GPS satellites that are orbiting thousands of miles above your head right now. This is seriously powerful stuff. You've cracked the code. You can now translate the world around you into solvable equations. You can measure things that are physically impossible to reach. So the only question left is, now that you can measure anything, what will you choose to solve?